Okay, we'll talk about simple pendulums now. These are kind of a little bit more intense than like a spring system or something like that. But I think that now with all the other stuff we've talked about in the previous three videos, we should be well equipped to deal with pendulums. So to start with, like we usually do when it comes to new situations, we have to make some simplifying assumptions. And those assumptions are first, that a string or rod that connects the pendulum bob to the pivot point is very light when compared to the bob's mass. So here is our pivot point here, this dot. From there, I have maybe a pendulum string that I've pulled, attached to that pivot point, and then attached to the pivot point and the string is a mass m. And so the mass of that string or rod for the pendulum is going to be much, much smaller than the mass of the bob. This thing here that hangs off the end is called a pendulum bob, which is short for bobbert, or if you're a European, it's short for Robert. Um, However, it's just an object that's there to just create like a mass. And so that mass will be acted upon by a gravitational force, which causes gravitational energy and all that fun stuff, where gravitational energy is going to take the place of spring energy from our spring objects that we talked about in previous videos. Second assumption we have to make is that the pendulum only moves in two dimensions, which means it swings left and right. It also, like if I'm here, here's my pivot point, and if I start, maybe I'm here at the bottom, here's my length of my string or whatever, and there's my mass of capital M. It's going to move maybe to here as I pull it back, and so it's moved in the Y direction, and it's also moved in the X direction. So these are the two directions it will move in. That means it won't make like a conical path or anything like that. Even if it did make a conical path, we could deal with it pretty easily. But just to keep things simple, we're assuming that it only swings in two dimensions back and forth. The third assumption is that the maximum angle from equilibrium is 15 degrees. So if I have my object, I'm just going to draw a dashed line to represent the halfway point. There's my pivot, here's my rod and or string and my mass. This angle here could be 15 degrees at most, and then this angle here could also be 15 degrees. And there's a reason for that, and we'll get to that in the next section, but we have one more assumption that we need to make. And that final assumption is that the friction in the pivot is negligible, and so is air resistance. Again, this means it's a conservative system. That's really what we're trying to get at, is that it's a conservative system, and so energy is transferred back and forth between different types, but no work is done to actually increase or decrease the energy of this pendulum system. Um, Now, usually we'll talk about like equations and quantities and things like that, but before we do that, I need to get something out of the way, and that is this thing called the small angle approximation. This is like just a math thing that'll um, we need to talk about real quickly. Um, what the small angle approximation is, or the small approximation or small angle approximation says that for angles less than 15 degrees, sine of theta is approximately equal to theta. In that if I have an angle that is like 1 degree, I can say that that angle, at least in radians, is equal to sine of theta. So here's a table that I made, and I did these calculations kind of quickly, so hopefully they are correct, but more or less they are, illustrate what's going on here. The angle for 1 degree is pi over 180 radians, which is point, if you approximate that in your calculator, you should get somewhere around 0.017453. If I plug that same angle, pi over 180, into sine of theta, I would get 0.017452. So not much of a difference there. And in fact, if we do a percent difference calculation, which that calculation would be percent diff is equal to the absolute value of sine of theta minus theta in radians divided by sine of theta plus theta divided by 2, all of that times 100%. This is a kind of like a percentage of how different these two numbers are from each other. If I do that percent difference, I get 0.005%. And this is not a mistake where it should be 0.5% because I didn't multiply by 100. It's really 0.005%. For a 5 degree angle, that would be that would be pi over 36 radians, which is basically 5 times pi over 180. Um, And then if I plug that into my calculator, you should get around 0.08727. Sine of theta is 0.08716 for 5 degrees. Percent difference there, 0.1, and you can see the rest. It goes up to about 15%. It's actually not like 1.0%. It's probably closer to more like 1.1%, but still that's pretty negligible, since what we do is very coarse grained. It's not like a very precise thing that we do in this class. So um, up to about 15 degrees, it is a very, very good approximation, and to a lesser extent, even up to about 30 degrees, where it's still under 5% difference. So those two numbers, the sine of 30 degrees and 30 degrees itself, at least in radians, the difference between those two is about 5%, less than 5%. I think it's close to like 4.7, 4.6%. So it's a good approximation for a lot of smaller angles, and we use that for a pendulum for a variety of reasons. It just simplifies so many things. So once we've talked about this small angle approximation stuff, next thing I want to do is I want to talk about a diagram of a pendulum. So our pendulum diagrams, we use these to kind of illustrate what the forces are going to do. So I'll make one side, and maybe these are our maximum amplitudes on either side of our equilibrium position. If I have a mass here, I would have, and I'm going to define my positive y to be in the direction upwards of the, in parallel to the string or rod. So this will be my positive y, and then my positive x has to be perpendicular to the string. My forces acting on this string are going to be a tension force that will be pointed along the string, Ft, and I will also have a force of gravity pointed downwards. And these are not to scale. Our Ft vector should be longer to match our Fg vector, but just looking at the directions is really the important thing here. So my y direction would go like this, and so I would get an Fgy here. I'm going to have to move my Fg symbols there. I'll put those back in a minute. And then I'd have an Fgx symbol, or Fgx vector there. And if I am at some maximum angle theta, this angle here for Fg, between Fg and Fgy, will also be theta. So what that tells us is that Ft and Fgy cancel each other out, whereas Fgx will cause us to go on that circular path. That's our radial acceleration. You could do this with the x and the y being our traditional like up and down, positive x to the right, positive y to the up, and that would just mean that our tension force would have to get decomposed, but it doesn't really matter. The idea is that there's either the tension or the gravity force, some interaction between them causes that radial acceleration, and then that the components that are parallel to each other for force of gravity and force of tension will cancel out, basically, keeping it stationary in the y direction. If I look at the other side, it would look very similar. Again, I'm good if my angles are, or sorry, if my directions are positive y is parallel pointed towards parallel to the string, pointed towards the pivot, my positive x needs to also be pointed inwards exactly the same way. So I've basically taken my coordinate system, I fixed it to the string, and now as the string swings, the coordinate system moves with it. And once again, I will have a tension force pointed along that string, Ft. I will have a force of gravity pointed down, Fg. I will have an Fgy point this way. That cancels out the Ft force. And then I will have a Ftx. That will cause my acceleration in the radial direction. And again, this angle here between Fg and Fgy is still that theta. So what we see here is that what we're really looking for, the force that's doing the work in this picture that we've drawn with our coordinate system, the force that is really keeping us on that circular path is that FGX. And if you look at where, or sorry, I think I screwed up my label down here. It should be FGX, not FTX. But FGX is the thing that really does the work here for us, that keeps us on that circular path. And so if I look at FGX, I can think, okay, it's opposite of my angle theta. So FGX is going to be my force of gravity times opposite. If you remember SOHCAHTOA, that tells us that sine is equal to opposite over adjacent. And so my, sorry, it's not opposite over, it's opposite over hypotenuse. So then my FGX, being the opposite leg of this triangle, would be FG times sine of theta. So I have an equation that says the force that is causing me to go on that circular path is Fg times sine theta. And this will be actually our net force, because the y components will cancel, or the y component will be canceled with the tension force. But since we're assuming that this pendulum is at most 15 degrees away from that equilibrium point, and since Fg is going to be the mass of the bob times g, we can just call it m times g times theta. That's that small angle approximation that we're using. But it turns out that if we want to talk about some other things, we can also think about the distance that this object will travel from. We can talk about in terms of a radial distance, and we can also talk about in terms of a linear distance. So the radial distance is going to be theta, right? That is our angle that we've been displaced from the equilibrium position. And the linear position, let's call that S for arc length. No, let's call that X because it's a horizontal position. So we'll call it X. Now, there's this other thing that I haven't really said anything about, and that is the length of the string. And if you remember from our uniform circular motion stuff, we had this arc length thing. And that said that our arc length, which is the distance that we traveled, linear distance we traveled, here we're saying it's x, is going to be equal to r times theta. Well, the radius of the circle is going to be the length of the string, and so we get x is equal to L times theta. And so my equation that I'm looking for is x is equal to L times theta, which I can then solve this for, oh, excuse me, I've messed up just a tad. That is not arc length. No, that's right. Arc length is L times, arc length should be L times theta, not L times x. So L theta is equal to x. That's what we're looking for. So if I solve this equation for theta by dividing through both sides by L, and I would get theta is equal to x divided by L, the length of the string on bottom and the horizontal distance we've traveled on top. But then I have this other equation that says my net force is mg theta. So if I plug in my x over L for that theta, what I would get is my net force is equal to m times g times x divided by the length of the rod. And there's one thing that's kind of important to point out here. It is dependent, this net force is dependent on the displacement or the distance x. If you recall, in one of the first videos, I had said that one of the assumptions that we have to make for harmonic oscillators, especially simple harmonic oscillators, is that the forces acting are proportional to the position. Here, what we see is our net force is indeed proportional to the position because, or even though gravity is not, doesn't have like a distance in it, right? As far as the force of gravity goes, it's just m times g. There's no y or x or theta in it. And we've figured out a way to use some simplification or some substitution and simplification to make it a function that has a position in it. And so now we can say this is a simple harmonic oscillator, you know, again, assuming there's no air resistance, no friction, all that stuff. The next thing that I want to do is I want to introduce a variable. I'm going to call this variable negative k. And why am I calling it negative k? Don't worry. I'm going to say that negative k is equal to m times g divided by L. And if I substitute that in, I would get my force is equal to mg over L, which is negative k, times x. And here we have an equation that is similar to our Hooke's law equation for springs. So indeed, this looks just like a spring equation. That's pretty cool, because if we didn't have it looking like a spring equation, this would not be a simple harmonic oscillator. This wouldn't really even oscillate at all. So if you remember back from when we talked about springs, I'm going to go to a new page here. If you remember back, we said that the period of oscillation for that was T is equal to 2 pi times the square root of mass over K. And let's see, I'm going to say that the force here is going to be moving in one direction, or is going to be opposite the motion. And so what I'm going to say is that the force itself, F net, or sorry, the net force itself, is actually going to be negative x times k, where k is now just m times g divided by L, because we need to have it fit into that Hooke's law formula, but we also need this mg over L to be a positive. But the reason why is because if I now take my my t and I plug in mg over L for that k in my t equation, what I get is t is equal to 2 pi times the square root of m divided by mg over L. And if I simplify this a little bit, my 2 pi stays the same. My L gets flipped and multiplied to the top. The m's cancel, and I get 2 pi times the square root of L divided by g. And this is the period of a pendulum, for a simple pendulum. This is an important equation. It could be asked of you on the AP exam. The other things that we can do is say that omega is equal to our frequency F, linear frequency, is 1 over t, so that'd be 1 over 2 pi times the square root of g divided by L, just flipping the L and the g. And then my omega, which is 2 pi f, is going to be just the square root of g divided by L. So all three of these equations are important, but I think for the AP Physics exam, the T equation is probably the most important. And if you ever needed the other ones, you could always use that F is equal to 1 over T to get the frequency equation, and that omega is then equal to 2 pi F to get our omega equation, square root G over L. But that's really all I wanted to get. Was that this frequency for a pendulum is basically the square root of g over L, and the frequency of a pendulum does not depend on the mass of the bob or any of this stuff. All it really depends on is the length of that rod and the acceleration due to gravity on whatever planet you're on. So you might be asked something like the omega, or the frequency omega was 5 on Earth, and then you go to another planet and now all of a sudden it's 25. So find the new gravity, or the new g value for this new planet, and then you could just kind of work backwards. You could take maybe your omega Earth divided by omega of the planet. You get the square root of g divided by L divided by the square root of some unknown g. We'll call it h, maybe h over L, because the pendulum length won't change. So my L's will cancel, and then what I get is that the ratio of omega of Earth on omega of the planet is equal to the square root of g divided by h. And then h again is that the acceleration on the new planet. From there, I could, plug in some numbers and stuff like that. I know g is approximately 10. I could square both sides of the equation, get omega Earth squared divided by omega planet squared is equal to g over h. I could solve this for h, which is the acceleration I'm looking for, and I would get omega planet squared divided by omega Earth squared times g is equal to my h value, and I could plug in numbers, which would be 25 squared divided by 5 squared times 10, and that would give me my new value for my gravitational acceleration. And then if you saw that this number was, and you can clearly see that this is going to be 25 squared divided by 5 squared is basically 25 times 10 is 250. And so what you see is that h is 250 times greater than g. If h is bigger, that means that the mass has increased. And so you would have a planet that's much more massive. Or maybe it says that the mass are the same between the two planets, Earth and whatever, and you could say maybe the radius of the planet is very, very small compared to Earth's radius. And so you'd be able to answer questions like that kind of conceptually. So that's it for simple harmonic oscillators and harmonic motion. I hope you enjoyed it. If you didn't, too bad, because it is pretty important for the AP exams. Um, well, I wouldn't say it's pretty important, but it might show up on one or two questions. So be ready for that. Anyways, we will see you guys on Monday, Tuesday, Wednesday, or Thursday or something. Whenever I see you next. Until then, have a good one.